Discussing the reductive elimination reaction of zirconocene alkyl hydride complexes into zirconocene and alkanes. The general equation for reductive elimination can be seen first, then followed by the general equation for reductive elimination of zirconocene alkyl hydride complexes. R in these equations represents the variable substituents, and they can be any of the examples displayed below. The reaction is important as reductive elimination is an important step in many catalytic cycles. It usually comes near the end of catalytic mechanisms, right before product formation. For some catalytic cycles, it's the turnover limiting step, making it very important to consider. The reaction is being done to see how cyclopentadienyl substituents influence the rate of reductive elimination. By manipulating the alkyl ligand, the effect can be analysed from the rate of alkane loss. This information could be used to further our understanding of pre-existing zirconocene alkyl hydrides and perhaps design new ones. To make the zirconocene alkyl hydride complexes, a straightforward addition took place of the appropriate alkyl lithium and zirconocene hydridochloride complex. The figure shows the general formation of the zirconocene alkyl hydride complex. Thermolysis of the zirconocene alkyl hydrides results in first-order elimination and cyclometallation of one of the cyclopentadienyl trimethylsilyl groups with only one diasterer of the cyclomethylated zirconocene hydride being observed. These reactions are best viewed as a composite of alkane reductive elimination followed by oxidative addition of a carbon-hydrogen bond of a trimethylsilyl substituent. The electrons in the zirconium hydrogen bond head toward the ligand R, and the electrons in the zirconium R head to the metal. A reductive elimination reaction has been claimed to be a composite of two reactions, namely reductive coupling of the alkyl and hydride ligands followed by a dissociation, and so an alternative mechanism with the possibility of sigma bond metaphysis is shown. Reactivity trends in reductive elimination are opposite to those of oxidative addition. More electron-rich ligands bearing electron-donating groups react more rapidly, since the ligands lose electron density as the reaction proceeds. More electron-poor metal centers bearing ligands with electron-withdrawing groups react more rapidly, since the metal center gains electrons. Sterically bulky ligands promote reductive elimination since the release of R and H can ease steric strain in the starting complex, so sterically demanding cyclopentadienyl substituents such as trimethylsilyl groups are used for their effectiveness in promoting alkane reductive elimination under mild conditions. On the whole, the oxidation state of the metal decreases by 2. Two new open coordination sites become available, and so a hydrogen R bond forms. Analysed by looking at the data collected from proton and carbon NMR spectroscopy and the rate constants. The more significant data was the rate constants, as they allowed a direct comparison between the different complexes, allowing a trend to be concluded. Additionally, it should be mentioned that recrystallization was needed to form the main reactant. When prepared as a blue impurity, could only be removed by recrystallization. The first-order rate constants for overall reductive elimination were measured by proton NMR spectroscopy at 60 degrees Celsius. The observed rate constants for reductive elimination for the different zirconocene complexes where the alkyl ligand was systematically varied can be seen in the table. In general, the rate of alkane formation increases as the steric disposition of the alkyl increases. This trend agrees with the theoretical expectations. To summarize, the reductive elimination of zirconocene alkyl hydride complexes into zirconocene and alkanes is an important reaction that sees a two-step formation of the product, first by alkane reductive elimination, and then oxidative addition of a carbon-hydrogen bond of a trimethyl substituent. And alternatively, there is the possibility for sigma bond metathesis. The reaction effect can be seen from analysis of the analytical data. Most significantly, the rate constants show the alkane formation increases as the steric disposition of the alkyl increases, just as expected.